Hello everyone, my name is Pranav Teja. Welcome to my Tech Talk. This is subject of linear algebra and calculus. The topic is system of equations. In mathematics, a set of simultaneous equations, also known as a system of equations or an equation system, is a finite set of equations for which common solutions are sought. An equation system is usually classified in the same manner as single equations, namely as system of linear equations, system of nonlinear equations, system of bilinear equations, system of polynomial equations, system of differential equations, or a system of difference equations. System of linear equations. In mathematics, a system of linear equations is a collection of one or more linear equations involving the same set of variables. For example, this is a system of three equations in the three variables x, y, z. A solution to a linear system is an assignment of values to the variables such that all the equations are simultaneously satisfied. A solution to the system above is given by x equal to 1, y equal to minus 2, z equals to minus 2. Since it makes all the three equations satisfied, the word system indicates that the equations are to be considered collectively rather than individually. In mathematics, the theory of linear systems is the basis and fundamental part of linear algebra. We look at some examples. Trivial example. The system of one equation in one unknown 2x equal to 4 has a solution x equals to 2. However, a linear system is commonly considered as having at least two equations. Some non-trivial example. The simplest kind of non-trivial linear system involves two equations and two variables. For example, these two equations, one method for solving such a system is as follows. First, take x equals to 3 minus 3 by 2 y. Substitute this expression for x into the bottom equation. Substitute this value of x in another equation. This results in the values of x and y. We'll get the value of y. General form. Now a general form of m linear equations with n unknowns can be written as this expression where x1, x2 up to xn are the unknowns, a11, a12, a12, amn are the coefficients of the system, and b1, b2 till bm are the constant terms. Often the coefficients and unknown are real or complex numbers, but integers and rational numbers are also seen, as are polynomials and elements of an abstract algebraic structure. Vector equation. One extremely helpful view is that each unknown is a weight for a column vector in a linear combination. This allows all the language and theory of vector spaces to be brought to bear. For example, the collection of all possible linear combinations of the vectors on the left hand side is called the span, and the equations have solutions just when the right hand vector is within that span. If every vector within that span has exactly one expression as a linear combination of the given left hand vectors, then any solution is unique. In any event, the span has a basis of linearly independent vectors that do guarantee exactly one expression, and the number of vectors in that basis its dimension cannot be larger than m or n, but it can be smaller. This is important because if we have m independent vectors, a solution is guaranteed regardless of the right hand side and otherwise not guaranteed. Now, matrix equation. The vector equation is equivalent to a matrix equation of the form Ax is equals to b, where A is an mn matrix, x is a column vector with n entries, and b is a column vector with m entries. The number of vectors in a basis for the span is now expressed as the rank of the matrix. This is the matrix equation Ax is equals to b. Now the solution set. The solution set for the equations x minus y is equals to minus 1 and 3x plus y is equals to 9 is the single point 2, 3. A solution of a linear system is an assignment of values to the variables x1, x2 till xn such that each of the equations is satisfied. The set of all possible solutions is called a solution set. A linear system may behave in any one of the three possible ways. If the system has infinitely many solutions, the system has a single unique solution, the system has no solution. Geometric interpretation. For three variables, each linear equation determines the plane in three-dimensional space, and the solution set is the intersection of three planes. Thus, the solution set may be a plane, a line, a single point, or the empty set. For example, as three parallel planes do not have a common point, the solution set of their equations is empty. The solution set of the equations of the three planes intersecting at a point is single point. If three planes pass through 2 points, their equations have at least two common solutions. In fact, the solution set is finite and consists in all the line passing through these points. For n variables, each linear equation determines the hyperplane in n dimensions. The solution set is the intersection of hyperplanes and is flat, which may have a dimension lower than n. The solution set for two equations in three variables. Now we'll look at the general behavior. The solution set for two equations in three variables is in general a line. In general, the behavior of a linear system is determined by the relationship between the number of equations and the number of unknowns. Here, in general means that a different behavior may occur for several values of the coefficients of the equation. In general, a system with fewer equations than unknowns has indefinitely many solutions, but it may have no solution. Such a system is known as an undetermined system. In general, a system with the same number of equations and unknowns has a single unique solution. In general, a system with more equations than unknowns has no solution. Such a system is also known as an overdetermined system. In the first case, the dimension of the solution set is in general equal to n minus n, where n is the number of variables and m is the number of equations. The following pictures illustrates this trichotomy in the case of two variables. The first system has infinitely many solutions, namely all of the points on the blue line. The second system has a single unique solution, namely the intersection of the two lines. The third system has no solution since the three lines share no common point. It must be kept in mind that the pictures above show only the most common case. It is possible for a system of two equations and two unknowns to have no solution if the two lines are parallel, or for a system of three equations and two unknowns to be solvable if the three lines intersect at a single point. Now, properties. Independence. The equations of a linear system are independent if none of the equations can be derived algebraically from the others. When the equations are independent, each equation contains new information about the variables, and removing any of the equations increases the size of the solution set. For linear equations, logical independence is the same as linear independence. For example, these two equations are not independent. They are the same equation when scaled by a factor of 2. This is an example of equivalence in a system of linear equations. For a more complicated example, these equations are not independent because the third equation is the sum of the other two. Indeed, any of these equations can be derived from the other two, and any of the equations can be removed without affecting the solution set. The graph of these line equations are three lines that intersect at a single point. Consistency. The equations 3x plus 2y equals 6 and 3x plus 2y equals to 12 are inconsistent. A linear system is inconsistent if it has no solution, and otherwise it is said to be consistent. When the system is inconsistent, it is possible to derive a contradiction from the equations that may also always be rewritten as the statement 0 equal to 1. For example, these two equations are inconsistent. In fact, by subtracting the first equation from the second one and multiplying both sides of the result by 1 by 6, we get 0 equals to 1. The graphs of these equations on the xy plane are a pair of parallel lines. It is possible for three linear equations to be inconsistent even though any two of them are consistent together. For example, these three equations are inconsistent. Adding the first two equations together gives 3x plus 2y equals to 2, which can be subtracted from the third equation to yield 0 equals to 1. Any two of these equations have a common solution. The same phenomenon can occur for any number of equations. In general, inconsistencies occur if the left-hand sides of the equation in the system are linearly dependent and the constant terms do not satisfy the dependence relation. A system of equations whose left-hand sides are linearly independent is always consistent. Putting it in another way, according to Rouse-Capelli's theorem, any system of equations is inconsistent if the rank of the augmented matrix is greater than the rank of the coefficient matrix. If, on the other hand, the ranks of these two matrices are equal, the system must have at least one solution. The solution is unique if and only if the rank equals the number of variables. Otherwise, the general solution has k free parameters where k is the difference between the number of variables and the rank. Hence, in such a case, there are an infinitude of solutions. The rank of the system of equations, the rank of the augmented matrix, can never be higher than the number of variables plus 1. Which means that a system with any number of equations can always be reduced to a system that has a number of independent equations that is at most equal to the number of variables plus 1. Now, equivalence. Two linear systems using the same set of variables are equivalent if each of the equations in the second system can be derived algebraically from the equations in the first system and vice versa. Solving a linear system. Uh, Describing the solution. When the solution set is finite, it is reduced to a single element. In this case, the unique system is described by a sequence of equations whose left-hand sides are the names of the unknowns and right-hand sides are the corresponding values. For example, x equals 3, y equals to minus 2, z equals to 6. When an order on the unknowns has been fixed, for example, the alphabetical order, the solution may be described as a vector of values like 3 minus 2, 6. For the previous example, consider the following system. These two equations. The solutions set to this system can be described by the following equation. For the first equation, x equals to minus 7z minus 1 and y equals to 3z plus 2. Here z is the free variable while x and y are dependent on z. Any point in the solution set can be obtained by first choosing a value for z and then computing the corresponding values for x and y. Each free variable gives the solution space one degree of freedom, the number of which is equal to the dimension of the solution set. Here, x is the free variable. Okay. Now, row reduction. In row reduction, also known as Gaussian elimination, the linear system is represented as an augmented matrix. This matrix is then modified using elementary row operations until it reaches reduced row echelon form. There are three types of elementary row operators. Type 1, swap the position of two rows. Type 2, multiply a row by a non-zero scalar. Type 3, add to one row a scalar multiple of another. Because these operators are reversible, the augmented matrix produced always represents a linear system that is equivalent to the general. There are several specific algorithms to row reduce an augmented matrix, the simplest of which are Gaussian elimination and Gauss-Jordan elimination. The following computation shows Gauss-Jordan elimination applied to the matrix above. This is the operation for this matrix. The last matrix is in reduced row echelon form and represents the system x equals minus 15, y equal to 8, z equal to 2. A comparison with the example in the previous section on the algebraic elimination of variables shows that these two methods are in fact the same. The difference lies in how the computations are written down. Now, Cramer's rule. Cramer's rule is an explicit formula for the solution of system of linear equations with each variable given by a quotient of two determinants. For example, the solution to the system is given by x equals to the coefficients. For each variable, the denominator is the determinant of the matrix of coefficients, while the numerator is the determinant of a matrix in which one column has been replaced by a vector of constant terms. Though Cramer's rule is important theoretically, it has little practical value for large matrices since the computation of large determinants is somewhat cumbersome. Indeed, large determinants are most easily computed using row reduction. Further, Cramer's rule has very poor numerical properties, making it unsuitable for solving even small systems reliably unless the operations are performed in rational arithmetic and unbounded precision. Matrix solution. If the system equivalent system is expressed in the matrix form Ax is equal to B, the entire solution set can also be expressed in matrix form. If the matrix A is square, has m rows and n is equal to m columns, and has full rank, all m rows are independent, then the system has a unique solution given by x is equal to A inverse B, where A, this is A inverse, where x is equal to A power plus B plus 1 I minus A plus A whole bracket W, where W is the vector of free parameters that ranges over all possible n into 1 vectors. A necessary and sufficient condition for any solutions to exist is that potential solution obtained using W is equals to 0 satisfy Ax is equals to B, that is that A plus B is equals to B. If this condition does not hold, the equation system is inconsistent and has no solution. If the condition holds, the system is consistent and has at least one solution exists. For example, in the above mentioned case in which A is square and of full rank, A plus simply equals A inverse and the given solution equation simplifies to this. As previously stated, where W has completely dropped out of the solution, leaving only a single solution. In other cases, though, W remains and hence the infinitude of potential values of free parameter vector W gives an infinitude of solutions of the equation. There are other methods. Now, homogeneous solutions. These are also homogeneous systems. A system of linear equations is homogeneous if all of the constant terms are zero. A homogeneous system is equivalent to a matrix equation of the form Ax equals to 0, where A is an m into n matrix, x is a column vector with n entries, and 0 is a 0 vector with m. Non-linear system. Now we have discussed about linear system. Now we'll come into non-linear system. In mathematics and science, a non-linear system is a system in which the change of the output is not proportional to the change of the input. Non-linear problems are of interest to engineers, biologists, physicists, mathematicians, and many other scientists because most systems are inherently non-linear in nature. Definition. In mathematics, a linear map or is one which satisfied both of the following properties: additivity or superposition principle. Additivity implies homogeneity for any rational alpha and for continuous functions for any real alpha. For a complex alpha, homogeneity does not follow from additivity. For example, an antilinear map is additive but not homogeneous. The conditions of additivity and homogeneity are often combined in the superposition principle. An equation written as fx is equals to c is called linear if fx is a linear map and non-linear otherwise. The equation is called homogeneous if c equals to 0. Non-linear algebraic equations, non-linear recurrence relations, non-linear differential equations, ordinary differential equations. Partial differential equations. Now, system of bilinear these are a type of system of equations called system of bilinear equations in algebra. System of bilinear equations are collective of equations, each one of which are written as bilinear form for which a common solution is sought. Given one set of variables represented as a vector g to the power t a I x equals to gi and another represented by a vector y, then a solution of system of bilinear equations for x and y can be written here. I is an integer whose value ranges from 1 to some upper bound r, and the a I r matrices and g I are some real numbers. System of bilinear equations arise in many subjects including engineering, biology and statistics. System of polynomial equations. A system of polynomial equations is a set of simultaneous equations f1 is equal to 0 till fh is equal to 0 where the fi are polynomials in several variables, say x1 to xn over some field k. A solution of a polynomial system is a set of values for the x is which belongs to some algebraically closed field extension k of k and make all equations true. When K is a field of rational numbers, K is generally assumed to be the field of complex numbers because the solution brings to a field extension of K which is isomorphic to a subfield of the complex numbers. System of differential equations. This is also a type of system of equations called system of differential equations. A system of differential equations is a finite set of differential equations. Such a system can be either linear or non-linear. Also, such a system can either be a system of ordinary differential equations or a system of partial differential equations.